Today I want to tell you about joint densities of random variables and joint distributions. All the word joint means is that we're going to be looking at more than one random variable at the same time and trying to understand how the probabilities of these multiple random variables can be calculated. As always, let's start with a story. The ranger was waiting for two comrades to arrive. Bored, the ranger began to model their arrival times. The first step was to give the arrival times names. T1 for the arrival time of the first comrade, and T2 for the arrival time of the second comrade. Furthermore, the ranger modeled T1 and T2 using a joint density. The density of T1 and T2 at little t1 and T2 would be 3/2 times the exponential function at -3t1 minus t2 over 2. All times the indicator that T1 and T2 were greater than or equal to 0. What was the probability that T1 and T2 fell into the Cartesian product 0 to 0.6 times 0 to 1.5? Another way of saying that is what's the probability that both T1 was between 0 and 0.6 inclusive and T2 was between 0 and 1.5 inclusive. Say that a random vector x sub 1 up through x sub n has a density with respect to product measure mu sub 1 times up through mu sub n if the probability that x sub 1 is in a little interval around mu sub 1 all the way up to x sub n is in a little differential element of mu sub n is equal to the density of x sub 1 up through x sub n at little x sub 1 up through little x sub n at the differential element of mu 1 up through the differential element of mu sub n. This differential notation means that if the goal is to find the probability that x sub 1 through x sub n is in a set A, just integrate the product measure over this region. So the probability that x sub 1 through x sub n is in a set A equals the integral over little x1 up through little xn being an A of the density of x sub 1 up through x sub n at little x sub 1 through little x sub n with respect to the differential of mu1 times the differential of mu2 all the way up to the differential of mu sub n. If the measure is counting measure, this integral just becomes a sum, as in one dimension. For example, suppose that the pair AB is in omega, where omega is the Cartesian product of the set 1, 2 with the set 1, 2, 3. Then AB has joint density F sub AB at little a and b equal to a plus 2b divided by 33 times the indicator that little a and b is in the set omega. What is the probability that capital B is less than or equal to 2? Well, to find the answer, sum the probabilities of elements of omega with b less than or equal to 2. These are the points 1, 1, 2, 1, 1, 2, and 2, 2. That means that the probability that b is less than or equal to 2 is going to be the density of a and b at 1, 1, plus the density of a and b at 2, 1, plus the density of a and b at 1, 2, plus the density of a and b at 2, 2. Which means that the probability that b is less than or equal to 2 is going to be 3 plus 4 plus 5 plus 6 all over 33, which gives you 18 over 33, or 6/11, which is about 54.54%. In the story, the density was given as the density of T1 and T2 at little t1 and T2 is 3/2 times the exponential function at -3t1 minus t2 over 2 times the indicator that T1 and T2 are greater than or equal to 0. So to find the probability that T1 is running from 0 to 0.6 and T2 is running from 0 to 1.5, this joint density is integrated over this region. Because this is a density with respect to Lebesgue measure, the integral is over a subset of r squared. The probability is equal to the integral over little t1, t2 in A of this density with respect to two-dimensional real space, where A is the Cartesian product of 0 to 0.6 times 0 to 1.5. Integrals in one dimension are easier to do than integrals in multiple dimensions. A theorem named Tineli's theorem tells us that whenever the integrand is greater than or equal to 0, as they always are with densities, you can use iterated integrals to find the integral. That means the problem of finding p, the probability that t1 runs from 0 to 0.6 and t2 runs from 0 to 1.5, can be written as an iterated integral, where we integrate t1 from 0 to 0.6 of the integral of t2 from 0 to 1.5 of the density 3/2 e to the minus 3t1 minus t2 over 2, then with respect to t2, then with respect to t1. The total dimension must be the same for the original and the iterated integrals. That is, if you started with one two-dimensional integral, you will end up with two one-dimensional integrals in the iterated version. To solve an iterated integral, work from the inside out. P equals the integral as t1 goes from 0 to 0.6 of 3/2 times -2 times e to the negative 3t1 minus t2 over 2, evaluated between t2 going from 0 up to 1.5 dt sub 1. That inside evaluates to -3 times e to the negative 3t1 minus 0.75 minus the exponential of negative 3t1. We can factor an e to the minus 3t1 out of that expression. In fact, let's factor a negative e to the minus 3t1, and we're left with 3e to the minus 3t1 times the quantity 1 minus the exponential of negative 0.75. Anti-differentiating now with respect to t1 brings down a factor of -3 in the denominator, which cancels with the 3 to give negative e to the negative 3t1 times the quantity 1 minus e to the negative 0.75, evaluated for t1 between 0 and 0.6. The result, the quantity 1 minus e to the minus 1.8 times the quantity 1 minus e to the negative 0.75, which is about 0.4404. Now, consider a random vector x sub 1, x sub 2, up through x sub n, where n is at least 2. Then the density of a particular x sub I is called a marginal density. To calculate these marginal densities, use the fact that the probability that x sub 1 is in a differential element around little x sub 1 can be written as the probability that x sub 1 is in a little differential element around x1, times x2 is some real number, x3 is some real number, and so on up through x sub n is some real number. This probability can be found by integrating out the variables that we do not want to be in the density. So to find the density of x sub 1, we integrate the joint density of f at x sub 1 up through x sub n at little x sub 1 up through little x sub n with respect to x sub 2, x sub 3, and so on up to x sub n, all from -infinity to positive infinity. A useful notation for a vector v with component I removed is v sub -I. For instance, if v is the vector 1, 2, 3, 4, then v sub -3 is the shorter vector 1, 2, 4. That notation makes the following fact easier to see. Let x be x sub 1 up through x sub n, and little x be little x sub 1 up through little x sub n. Given the density f sub big X of little x of the random variable big sub x, the density of x sub -I at little x sub -I is the integral over x sub I in all real numbers of the joint density of the entirety of x at little x with respect to the measure of the ith component. If you want to remove all but one random variable in the vector, integrate out every random variable except the one that you wish to keep. For example, suppose as before that AB is in omega, where omega is the Cartesian product of the set 1, 2 and the set 1, 2, 3 with density f at little a and b is a plus 2b divided by 33 times the indicator that a and b is in omega. Now suppose that we're after the density of a. Well, to get the density of a, we integrate out b. Because we are working on discrete random variables, integration becomes summation. So the density of big A at little a is the sum, as b runs from 1 up to 3, of the joint density of a and b at little a and b. So that sum becomes a plus 2 over 33 plus a plus 4 over 33 plus a plus 6 over 33 times the indicator that little a has to be between 1 and 2. Adding those together, we get 3a plus 12 over 33, and canceling out a 3 leaves us with a plus 4 over 11 times the indicator that a runs from 1 to 2. On the other hand, to get the density of b, we integrate out the random variable a. That gives the sum over a running from 1 up to 2 of the joint density. So we get 1 plus 2b over 33 plus 2 plus 2b over 33 times the indicator that b is either 1, 2, or 3, which reduces to the density of big B at little b is 3 plus 4b over 33 times the indicator that little b is either 1, 2, or 3. For example, let x, which is x sub 1, x sub 2, and x sub 3, have joint density 1/48 times the quantity x sub 1 plus 2x sub 2 plus 3x sub 3 times the indicator that x1, x2, and x3 are all between 0 and 2. What is the density of x sub 2? To answer that, let a be 0,2 times 0,2 times 0,2, and g of x be 1/48 times the quantity x sub 1 plus 2x sub 2 plus 3x sub 3. So the density of big X at little x is g of x times the indicator that x is an a. The indicator will change the limits of integration, and the g of x then is the part that varies with x. To find the density of x sub 2, it is necessary to integrate out both x sub 1 and x sub 3. So our integral is going to be the integral over x sub 1 from negative infinity to infinity, x sub 3 from negative infinity to infinity, of g of x times the indicator that x is in a with respect to x3 and then with respect to x1. We can use the indicator function to change the limits. So the density of x sub 2 at little x sub 2 is the indicator that x sub 2 is from 0 to 2 times the integral as x1 goes from 0 to 2 of the integral as x3 goes from 0 to 2 of g of x dx3 dx1. Let's do the inside integral first. We'll say I sub 3 is the integral as x3 goes from 0 to 2 of g of x. We have to anti-differentiate g of x to get 1/48 times the quantity x sub 1 x3 plus 2x2 x sub 3 plus 3/2 x sub 3 squared, evaluated as x sub 3 runs from 0 to 2. This simplifies to be 1/24 times the quantity x sub 1 plus 2x sub 2 plus 3. Notice that at this stage of the game, there are no x sub 3's left. We've integrated them out. To get to then the density of x sub 2, we take that I sub 3 value and we integrate out x sub 1 from 0 to 2. When we do that anti-differentiation, we end up with f sub x sub 2 at little x sub 2 being 2 plus little x sub 2 over 6 times the indicator x sub 2 runs from 0 to 2. Joint densities can also be used to show independence. Suppose that x has density f sub x of little x with respect to mu1, y has density f sub y of little y with respect to mu2, and their joint density has the form of the product of their individual densities. Then consider a set A measurable with respect to x and B measurable with respect to y. If we calculate the probability that x is in A and y is in B, we can take the joint density and write it as the density of x times the density of y. We can take our two-dimensional integral and make it into two iterated one-dimensional integrals. But now x doesn't depend on y at all. So we can factor it out of the inner integral and it joins the outer integral. But now the inner integral is just the density of y at y evaluated with respect to mu2 over y in B. And that's just another way of saying the probability that the random variable y is in B. Now that doesn't depend on x, so we can factor that out of the integral involving x, and we're left with the integral for x and a of the density of x at x, which is just the probability that the random variable x is in A. So what we've shown is if we have a joint density that factors into the density of x times the density of y, then x and y have to be independent random variables, which is a very powerful fact. It turns out that it works in both directions. If we have a density that factors into two pieces, f sub 1 and f sub 2, then the density of x has to be proportional to f sub 1, and the density of y has to be proportional to f sub 2. For example, suppose that the joint density is 2e to the minus x minus 2y times the indicator x is greater than 0 and y is greater than 0. Can we show that x and y are independent? Well, we notice that we can factor the joint density into a piece that only depends on the dummy variable for x and one piece that only depends on the dummy variable for y. Hence, they're independent. To be precise, this joint density can be written as 2e to the minus x times the indicator x is greater than 0 times e to the minus 2y times the indicator that y is greater than 0. So that's how you deal with joint densities. Densities for more than one random variable at a time. See you next time.